The goal of the ASHRAE Integrated Sustainable Building Design is to design a self-sustaining meteorological station. The idea is to design a building that is able to give the best return on investment after 50 years, and it has to satisfy the ASHRAE standards as well as the owner requirements.
Renewable energy is how we are achieving our net zero goal. The idea is to build a building that generates as much energy as it uses without any carbon being emitted in the process. The overall system that we came up with used solar, wind, it has a connection to the grid, and then we also have it hooked up with a propane generator backup.
The building site is located on a 94-acre island between the southern tip of Chile and Antarctica. The way we figured out what the best envelope was is we first simulated a 90.1 2016 baseline. Once the baseline was established, we ran a simulation on that, and that gave us a base to compare everything against. From there, we changed one material at a time and ran simulations, and that way we could know what each changed, how it affected the heating load and subsequent energy efficiency. So one of the most important things about the building envelope is the foundation. Because the earth is cold there, the more that you increase the insulation value, the more energy savings you see. So for the walls of the building, we tried 5 different types. So after running simulations on each wall type to see how much energy each one used on an annual basis, we found that the wood frame wall with the continuous insulation on the outside was actually the most efficient. For the roof, what we did is we tested everything against the baseline. We found out quickly that you don't have to improve the roof at all over 189.1. It's good enough as is, just build it like that and you're good to go. So after we ran simulations and found out what the best building envelope materials were, we put them all together into a single model, ran the simulation again, and proved a full 30% savings in energy. That 30% savings in energy, even when considering the additional initial cost of the more expensive building materials, will save the owner $725,000 over the life of the building.
So one of the main components of the building is sustainability. One of the things that we looked into was light pollution and the recyclables, like the locations where we were going to have recyclable bins in the building. And finally, it was the shading.
My responsibility was to meet ASHRAE 189.1 indoor environmental quality, which includes ASHRAE 62.1 on ventilation and ASHRAE 55 with thermal comfort.
Having a large source of hot water in the center of the occupied space inspired a very efficient HVAC system. The tank we chose allows you to store water at 180 degrees Fahrenheit, and heat is transferred from the tank to make 100-degree water that we will pump through little polyethylene tubes in the concrete foundation. Your foundation becomes a large thermal mass that stores heat energy, and water moves more heat than air does. Because radiant heat provides silent, even heating, zoning is not as much of a priority. But we still broke the building up in zones based on different occupancy types by using balancing valves to adjust the flow rate of the water. Radiant floors are known for their superior comfort levels, and simulations in the IES virtual environment prove that the percentage of people dissatisfied with the thermal comfort per ASHRAE 55 was less than either of the forced air systems that we tested, even at a lower temperature set point. Although the radiant floor is an ideal choice for heating the building, it doesn't provide any ventilation or humidity control. For these two important considerations, a dedicated outdoor air system, or DOAS, was chosen. We chose a DOAS system because they are ideal ventilators that deliver 100% outside air to each zone of the building instead of stale, recirculated air that contains reduced oxygen and increased carbon dioxide levels. This type of system allowed us to exceed the air change requirements of ASHRAE 62.1. The system works by first bringing in fresh outside air, filtering it, and running it through an energy recovery ventilator. Once some of the heat energy is transferred to it from the exhaust air as it exits, the warmer incoming air is run through a tempering coil to precondition it further. The coil is fed with hot water that is heated by the building's thermal storage system. There's also a direct expansion cooling coil to handle the small cooling load on the building if necessary. A psychometric analysis of the climate revealed that the island's humid and cold outside air doesn't hold very much water, so even though the outdoor relative humidity is about 90%, by the time it's heated to the required 73 degrees inside, it drops 20%. Because of this, a steam humidifier is the last preconditioning step that the outdoor air goes through before being delivered as fresh air to the spaces. The system is optimized using demand control ventilation to reduce unnecessary airflow to spaces such as the conference room and learning center when they are not occupied. To achieve this, occupancy sensors are used to send airflow only where it is needed. Simulations that were done in IESVE Pro to compare the two alternative options against the 90.1 baseline proved that the Radiant Floor/DOAS system saved about 30% from the baseline. Considering it with the high performance envelope, energy consumption is reduced by 59%. With this amount of energy being saved, the owner will break even on their additional investment after only 8 years and will save $1.4 million over the building's 50-year lifespan.
So for the water use efficiency, we first look at the standards, and then we look at the resources on site to see what we can use to reduce the water consumption even more. By looking at the climate, we noticed that there's a lot of rainfall. So in order to reduce the amount of water used on site even more, we're going to use the rainwater harvesting to reduce our overall water consumption, in addition to WaterSense products and Energy Star appliances. So for our rain harvest water system, we first collect the water and it goes through an initial filter. After that, it gets stored into a cistern. Then the water can be used for gray water for flushing. Now, if you want to do more to those collected rainwater, it would go through another filter, a 5-micron filter to be precise. After that, it would have to go to a UV purifier, and then it can be used for drinking water, it can be used for the cold water supply, to shower, or anything you can think of.
Simulations were used to determine the best lighting environment for the building, and we compared different lighting fixtures like fluorescent, incandescent, and LED. We used the standards to be able to use which power densities were appropriate for each zone. Based on that, LED were the ones selected. So for the external lighting, one of the things that we needed to have in mind was light pollution, and we based our selection based on the standard for the International Dark Sky Association. So the light fixtures that were chosen needed to meet those standards, and most of the lights are going to have their LED lights, and they're going to have motion control where they would turn off automatically if there was no one there.
USGBC, United States Green Building Council, a relatively new organization in standard setting, spearheaded a program called LEED, and it's Leadership in Energy and Environmental Design. And it has given a very easy metric to measure how green, how sustainable, how energy efficient a building is. There were a lot of points within LEED that we simply had to take a punt on. There was no way we could make a claim for them because of our location. There's a lot to do with LEED that really aims at building a more sustainable community in an urban area, and we are in the least urban area you can possibly imagine. For sustainable sites, we had to look really hard at the environment that we were on, and that includes some endangered species. We have albatrosses, brown albatrosses, that are genuinely an endangered species, and we're talking about putting windmills up to generate our electricity from sun up to sundown during the times of year that these albatrosses are migrating. We're going to shut down our wind turbines. We're going to make sure they're not running, and we're going to keep these birds safe while also supplying renewable energy to our building. There's always a compromise. There's always a way to make it work, and we found that way. Energy and atmosphere. Again, our renewable energy resources, we have covered the gambit. We have a completely renewable system that has absolute backup and will never shut down. And any time that we don't have renewable resources, we've developed a plan to purchase carbon offsets so that we can trade the carbon that we do use with other groups that are greener and sustainable and have extra to trade. And we can make sure that the balance on the globe is met through those cap and trade and through that carbon offset purchasing program. Indoor environmental quality with our building automation system. with our intelligent HVAC design, with our radiant floors, we are adamant about ensuring the comfort of all of the occupants in this building. We have exceeded ASHRAE 55.1 option. We have exceeded it in every regard, and we're able to claim the vast majority of the LEED credits there. We missed one or two there, again, because of our location-specific problems. The innovation credits were personally the ones I was most excited about getting, because it meant we were thinking about the problems in a new way. We have put in a lot of hours into this project, and I really have to say, as we're walking away from it, we've put together a good building. This is, aside from all the ticking of the boxes to make sure we hit the codes, this is an energy-efficient, sustainable design that would serve these customers well beyond the lifespan that they specify.